Good morning, friends. We are learning our subject Machine Learning 3170724. In that, we are learning the module 6. It is Bayesian concept learning, right? So, now we want to learn Bayes theorem and concept learning. So, let's see one simplistic view of concept learning can be that if we feed the machine with the training data, then it can calculate the posterior probability of the hypothesis and outputs the most probable hypothesis. This is called brute force Bayesian algorithm. What we say is the if we feed the machine with training data, then it can calculate the posterior probability of hypothesis and outputs the most probable hypothesis, right? And this is called the brute force Bayesian learning algorithm. It is also observed that consistency in providing the right probable hypothesis by this algorithm is very comparable to the other algorithms. Let us see about what is there in brute force Bayesian algorithm. Say how to use the map. What is map? India ka map? या गुजरात का मैप नो इट इज maximum a posteriori. So how to use map hypothesis output to design a simple learning algorithm, that is the brute force map learning algorithm. So what we are having, let us assume that learner considers a finite hypothesis space H in which the learner will try to learn some target concept. We are having the hypothesis space H, and what is that learner will try to learn some target concept. Okay, so let's see concept C, that is it is having say function that is x, then what do we say is domain is x, and 2, that is the range typically we used to say is 0 comma 1, where x is the instance space corresponding to h. The sequence of training examples is say x1 t1, x2 t2, xm tm, where xi is the instance of x and ti is the target concept of xi, and which is defined as ti is equal to c of xi. Without impacting the efficiency of the algorithm, we can assume that the sequence of instances of x, that is x1, x2 up to xm, is held fixed, and then the sequence of target values becomes t is equal to t1 to tm. For calculating the highest posterior probability, we can use Bayes' theorem as discussed earlier. Calculate the posterior probability of each hypothesis H in hypothesis space H. So what do we say about that? P of H by T. That means the probability of H based on T occurred, right? So that is equal to P of T by H into P of H upon P of T. This we know from the Bayes theorem, isn't it? So that's what we are putting here. Now H map. What is map? that is maximum or posterior, right? Whichever is the maximum posterior probability, that's what we want to choose. So that is equal to argmax. We know that argmax will give us the maximum probability, isn't it? So that is H belongs to H, and we consider P of H by T. Whatever are the P of H by T probabilities, in that whatever is the maximum, that will select, and that is the H map. Okay. For example, let me say you that we are having, say, Bayes computer example. Let me say we are having simple, that is Bayes computer example. Now over there, we say that if a person is student, he will have the computer. Suppose I am saying that he will purchase the computer, right? Okay. So what? Bayes computer, for that we need to find that whether a person will buy computer or not. Will buy computer or not, right? This is what is our decision, that whether a person will buy computer or not. Now see, if we are having the data from which we can say that if a person is student, he will buy computer. Now say a person is not student means any other, then you can say for not student, we can say we can be having the conditions like his credit rating is fair or not. If it is fair, then we can say that it is credit rating is fair. Then you can say that person will buy computer. So buy computer will be yes, right? Otherwise, we can say it is no, right? So if we are having the data, something like this, what we can say is after this data, we have analyzed. We want to know that if a person is say lecturer, and that person's credit rating is low, then will that person buy computer? So what we have to do is we have to find the probability for Bayes computer is equal to yes, Bayes computer is equal to no for all the things, that is all the characteristics, all the parameters which are given. So lecturer is that is a person is lecturer and credit rating is low. So based on this, we would like to find the probability, that is of Bayes computer. Yes, then what is the probability? Bayes computer is equal to no, then what is the probability? And after that, whichever is maximum from both the things, that will be the real result, right? So let me say that for Bayes computer is equal to yes, the probability is say 0.5. And we can say that probability of Bayes computer is equal to no, we find then that is equal to 0.7. Now from this, we can understand that P no is 0.7, which is maximum, right? So for that, we can say that lecturer will not buy computer. Only lecturer? No, not from the person, but his credit rating is also low. So whatever are the characteristics given or whatever are the parameters given, for all of them we will find the probability, will multiply them, and then after we'll be able to find them as whether they'll be having the probability of yes as what, no as what, because we are having two classes, that is whether person will buy computer or not, right? So for both the classes, we'll find the probability. Whatever is the maximum, that we will choose as the answer, that whether the computer will buy, whether the person will buy computer or not. Fine? Okay. So let us proceed. We are learning brute force Bayesian algorithm. Okay. Okay. So let us try to connect the concept learning problem with the problem of identifying the edge. On the basis of the probability distribution of P of H and P of T by H, we can derive the prior knowledge of the learning task. There are few important assumptions to be made. How? Let's see that. The first assumption says that the training data or target sequence T is noise free, which means that it is a direct function of x, and that is Ti is equal to C of xi, right? That we have already seen. What we are saying is the training data or target sequence T is noise free. Is it the real case? Actually not, but these are the assumptions we are making, right? So target is noise free and training data. For that also what we are saying, either this or this is noise free. Second assumption says that the concept C lies within the hypothesis space H. Third one is each hypothesis is equally probable and independent of each other. Say bias computer is equal to yes is one hypothesis, and the second is bias computer is equal to no. So what we are saying is both the hypotheses for our example are equally probable. That is 1 by 2 we can say. If we are having 2 only, then we can say 1 by 2, that is 0.5, and independent of each other. We do not have any relation between them. That is what is the assumption. Now, on the basis of assumption 3, we can say that each hypothesis H within the space H has equal prior probability, and also because of assumption 2, we can say that these prior probabilities sum up to 1. We can write P of H is equal to 1 by H. As I told you, for our example, only 2 hypotheses are there. So we have considered the probability as 1 by 2. So here if we are having say H probabilities, then we will say them as 1 by mod H, and for all H within the hypothesis space. Fine. This mode is mode of H, that means the count of the hypothesis inside the hypothesis space. Okay. Now, P of T by H is the probability of observing the target values Ti in the fixed set of instances. They are the x1 up to xn in the space where H holds true and describes the concept C correctly. Using assumption 1, we can say that if T is consistent with H, then the probability of data T given the hypothesis H is 0 and 1 otherwise, right? Either it can be 1 or it can be 0, isn't it? So P of T by H is equal to 1 if Ti is equal to H of xi for all Ti within T and 0 otherwise, right? Using the Bayes theorem to identify the posterior probability, what we are having is P of H by T is equal to P of T by H into P of H upon P of T. This is always the case, isn't it? For the cases when H is inconsistent with the training data T, we get P of h by T that is equal to 0, that is for P of T by h, into P of h upon P of T. So that will be equal to 0. It is but obvious. What we are saying is when h is inconsistent with the training data, then this P of T by h will be equal to 0. Fine. So ultimately, P of h by T also will become the 0, isn't it? When h is consistent with T, then what is the case? Then we can say P of h by T that is equal to 1 into 1 upon h divided by P of T. So that will be equal to 1 upon mod h into P of T. Now if we define a subset of hypothesis H which is consistent with T as HD, then by using the total probability equation we can get P of T that is equal to sigma Hi belongs to HD, P of T by Hi into P of Hi. So what we do with that? We are putting the value that is 1 into 1 upon mod H. Then plus what we say is sigma Hi does not belongs to HD, 0 into 1 upon mod H. Right? This is what we have already calculated before. Right? So we can have the idea. Fine. So after that, we can say 1 into 1 upon h because this term becomes 0, and that is equal to what do we say is mod of hd upon mod h, right? So what do we say is after that p of h by t that will be equal to 1 upon mod h into mod hd upon mod h. This is what we have calculated, right? So for this one p of t we are putting the value. Okay. So in this equation, we have put these values and we are getting it as it is equal to 1 upon HD, right? Okay. So, with our set of assumptions about P of H and P of T by H, we get the posterior probability that is P of H by T as we have just seen that, right? So what we are getting it as? It has the value that is 1 upon mod HD, right? So with our set of assumptions about P of H and P of T by H, we get posterior probability P of HT, that is P of H by T as P of H by T that is equal to 1 upon mod HD if H is consistent with target T or otherwise it is 0. Fine, we have just seen that. We have calculated that also, right? Where H is the number of hypotheses from the space H which are consistent with the target set T, isn't it? The interpretation of this evaluation is that initially each hypothesis has equal probability. And as we introduce the training data, the posterior probability of inconsistent hypothesis becomes 0 and the probability, that is the total probability that sums up to 1 is distributed equally among the consistent hypothesis in the set. So under this condition, each consistent hypothesis is a map hypothesis with posterior probability of 1 upon mod HD. Now, we want to learn the concept of consistent learners. Why? Because here in the brute force Bayesian algorithm, we have considered the h is consistent with t and we are getting the value, or otherwise it is 0, right? So for 0, what to consider? Nothing, isn't it? So where the value is at, for that, let us learn next. Okay. So what do we say is concept of consistent learners. From the discussion which we have done, where what do we say is the P of h by t is 1 upon mod h d, right? For consistent learners. Okay. So the behavior of the general class of learner whom we call as the consistent learners. That is what we have seen, isn't it? So the group of learners who commit zero error over the training data and output the hypothesis are called the consistent learners. Group learners who commit zero error over the training data and output the hypothesis are called the consistent learners. Fine. If the training data is noise free and deterministic, what do we say? P of d by h, that is equal to 1. If d and h are consistent and 0 otherwise. If there is uniform prior probability distribution over h, so P of h will be, P of h1 will be equal to P of h2, right? This is h1 and h2 for all m and n. Then every consistent learner outputs the map hypothesis, right? So let me say this is h1, say, and this is say h2, right? Or m and n we can say, isn't it? In general, we can say this is m and this is n. hm and hn, right? So an important application of this conclusion is that Bayes' theorem can characterize the behavior of learning algorithms even when the algorithm does not explicitly manipulate the probability, as it can help to identify the optimal distributions of P of h and P of t by h under which algorithm outputs the map hypothesis. The knowledge can be used to characterize the assumptions under which the algorithms behave optimally. The theorem can be used with the same effectiveness for noisy training data and additional assumptions about the probability distribution governing the noise, right? What we are saying is we have first assumed that the training data or the target is noise free, but it is not always the case, right? But but we say that the theorem can be used with the same effectiveness for the noisy training data, right? And additional assumptions about the probability distribution governing the noise. So whether it is noise free or noisy, than two we can apply it, right? We have started with the assumption that it is noise free, that is the training data or the target, but then after we can say that we can apply to noisy data too. Now the next thing which we want to learn is Bayes optimal classifier. What is that and why should we use it? Bayes optimal classifier is a probabilistic model that finds the most probable prediction using the training data and space of hypothesis to make a prediction for a new data instance. Why Bayes optimal classifier? What we are saying is most probable prediction, right? That is the Bayes optimal classifier. Now, why Bayes optimal classifier? So, what we say is it can be shown that of all classifiers, the optimal Bayes classifier is the one that will have the lowest probability of misclassifying an observation. That is the lowest probability of error. So, if we know the posterior distribution, then using the Bayes classifier is as good as it gets, right? So, we can say that the optimal classifier, why is it called? Because it finds the most probable prediction using the training data and space of hypothesis, right? To make a prediction for new data instance. See, whatever data is there, from that we analyze the things. Then after we predict for the new data instance, right? As we have already discussed that the data was given for a student and not student. We have find the data that is for lecturer and his credit rating was low. For that we find, right? I have given you the example. We haven't yet calculated the probability, and you can say from that we should be able to predict whether person will buy computer or not. That example will see for the special classifier, that is our Navy based classifier, which also uses the Bayes theorem, right? So let us learn all these things first, then after we'll see the example of it, right? So what do we see about the Bayes optimal classifier? We have just started with. Let us understand that using the example to illustrate the concept. Let us assume three hypotheses. They are say H1, H2, H3. In the hypothesis space, that is H. Let the posterior probability of this hypothesis be zero point 0.4, zero point 0.3 and zero point 0.3 respectively. See, we haven't calculated, okay? We are assuming that three hypotheses are there and their posterior probability is zero point 0.4, zero point 0.3 and zero point 0.3, right? Now there is a new instance X which is classified as true by H1 but false by H2 and H3. Then the most probable classification of the new instance X can be obtained by combining the predictions of all hypotheses weighted by their corresponding posterior probabilities. Fine. So, by denoting the possible classification of the new instance as C from the set, capital C, the probability P of Ci upon T, that the correct classification for the new instance is Ci and is the optimal classification for which P of Ci by T is maximum, right? So how we can find that? That is P of Ci by T, that is equal to sigma Hi belongs to H, P of Ci upon Hi into P of Hi by T, right? I told you that we have to find the production of these things, isn't it? Then after, what do we say? The optimal classifier is for which Bayes optimal classifier is equal to argmax, isn't it? Of sigma. Addition we have to do. See, for first thing is we are doing the production here, and then after we are doing the summation of all such probabilities, isn't it? So here what we have to do is Bayes optimal classifier, that will be equal to R max of what term we have considered here, right? So argmax now we have to consider for each concept. For Bayes computer is equal to yes and Bayes computer is equal to no, we are having two concept, or you can say two classes. They are Bayes computer is equal to yes and Bayes computer is equal to no, right? So for that we'll find the maximum posterior probability, and that will give us the Bayes optimal classifier, right? So extending the example, the set of possible outcomes for the new instance X is within the set C, that is equal to true or false. And P of H by T, that is equal to zero point 0.4. P of H by T, oh, this is H1, H2, H3, isn't it? This is H1, this is H2, and this is H3, isn't it? So this is also H1, this is H2, and this is H3. Same way here also. This is H1, this is H2, and this is H3, right? See, subscript is many a times being removed, right? And so we have to correct that. Okay, so P of H1 by T is 0.4 that we have already assumed, right? This is 0.4, 0.3, 0.3, right? That is what we have already assumed. So that's what we are putting here. That is P of H1 by T is 0.4, P of H2 by T is 0.3, P of H3 by T is equal to 0.3, right? Now P false upon H1, P false upon H2, P false upon H3. That's what we have to find, right? Based on this hypothesis, this is false. Based on this hypothesis, this is false. Based on this hypothesis, this is false. Then what? Then that probability is say 0, 1, 1. Same way, we have to find the probability of true based on H1, H2, and H3, right? Bayes computer is equal to yes is true. Bayes computer is equal to no, that is false, right? So we are finding that whatever are the probability. Now what we have to do is we need to find is based on the production and summation, we find both the cases, that is for true, for the false, and after that we'll be taking the maximum probability, that is the argmax, isn't it? And argmax says that this true probability is 0.4 and false probability is 0.6. So whichever is the maximum, this 0.6, isn't it? 0.4 and 0.6. So we can say that 0.6 is maximum. And so the answer or prediction for this new instance X is false, right? Because it is having the maximum probability. Getting it? This method maximizes the probability that the new instance is classified correctly when the available training data, hypothesis space, and the prior probabilities of the hypothesis are known. This is also called as the optimal classifier. This is what we are studying, right? So Navy-based classifier, for that we'll be learning the examples. Okay, so that's all for today.